on this axis I want to see here. So as a function of time, what really happens is that this omega that we have here, for the most part, is zero, meaning nothing actually happens to our qubit, right? And then once we get to the point in our circuit where we want to implement this gate, we turn it on to some specific value, then it's that specific value for some time, and then we turn it back onto zero. So now, because if it's zero, our Hamiltonian is zero, nothing happens to our qubit, so our qubit just stays the same from here to, so I can maybe draw it like this. So here we would have, let's say, psi, and at this point here again, psi is unchanged. Now we turn on the interaction, meaning we take omega from some value 0 to some value that we have fixed in our experiment or in our quantum computer. It's constant for that value for some time. And then after this, at this point here, we have precisely characterized this time step here, let's call it tau, such that at the end we have psi, or the quantum state is sigma x times psi. And then again, the Hamiltonian is 0, so all the way over to this point, it's still the same, meaning it's this sigma x psi. And then you could turn on again if you want to do one more x gate, maybe for half the time, then it would be different gate and so on. Does it make sense?
Yes, I think I get it. So it's like you're using a filter on the signal, for example.
Yes, correct. And yeah, we will come back to a few examples later in the course, like how can you really physically do these gates, like what are the materials and what are the electronics that you use to generate these things. But for now, it's a bit more abstract in the sense that you can really just think of it as this.
May I ask, so this was really helpful, by the way, because I was also wondering about the hardware and if we do learn something about it. Now, is it always the case that we take omega as 0 and then we have sort of this step function implemented with the gate?
So now since you ask, it becomes a little bit technical, but actually no, this is rarely actually the real case, because it turns out that I don't know how much you're into sort of electronics, but actually let's make the real case here. So what really happens in most instances is that instead of going from 0 in some step function, what you actually do is you apply a pulse that may look something like this. And why is this? That's because if you have anything electronics going from 0 to some value in infinitely short time, you just can't do in real electronics. So you instead try to go sort of smoothly up, and you also need to then have a finite frequency of your signal. So it is sort of what we call a Gaussian envelope, like this, that you modulate with some cosine. And this is how it looks in real life. But, and this is important, what matters is not so much the shape. The shape actually is completely, does not change the interaction, because what really matters for the gate here is actually the integration of, if we think of omega t dt from, if we call this time ta, and this time t. So if we integrate from TA to TB, this is what matters. So if you have a constant pulse with some integral over it, meaning some area under the curve here, that is some specific value. If you do sort of a smooth thing here and have the same area, you really get the same thing. So while technically you don't do the square pulse, what you do is really formally the same. Does that answer the question? I know I was a bit at the side and maybe it's too much detail.
Yes, no, I liked it a lot. Thank you. Just briefly to understand, if we had a Z gate now, for instance, we would switch the sign, right, instead of the amplitudes. On the left, the equation that you wrote.
Yeah. So okay. So yeah. So what you could maybe think, just to think of that, right? So what you could think of is your Hamiltonian. You could have more terms. So here you could have a h bar. Let's call that over here, z half, and then you could, for example, here later on you could turn on your z part. Then that would implement a z gate, and then maybe you would have a y term in your Hamiltonian, and then later on you could turn on your y pulse, and then you would have a y gate. So by turning on and off sort of different type of interactions in your Hamiltonian, you can get different types of gates. Now I didn't say what the Z and Y gates are, but they are just the application of the yeah, they are here. So now they are on top of my drawing, but they are just the sigma y and sigma z operators that you've seen. So the way you go between different gates is you turn on different interactions. Does that answer the question?
To some extent, yes, but what I was also referring to is on the left where you drew the X gate with the green arrow.
Yeah.
The effect that it has is that it changes the alpha and beta, right?
Yeah. So the X gate is a bit flip, right? And then you're right, the Z gate. Now we are jumping a bit ahead. So let me just go here. I will save this drawing. And then let me clear everything. And then let's go on. Yes. So indeed, what you say that the X and Y gate, they look different. So here you see how the Hamiltonians look, and then let me go to my whiteboard here. Let's make a new drawing here. So indeed, so if we start with our X gate, indeed, what happens is that we have our circuit here. We have X, like this, and if we have alpha 0 plus beta 1, then on the other side we get beta 0 plus alpha 1. Now, I think what you said is that in the Z gate, what we do is, of course, change the sign. But the Z gate here has the matrix 1, minus 1, 0, 0. So if we have alpha 0 plus beta 1, what comes out on the other side is alpha 0 minus beta 1. So what we do here is really what we call a phase gate, or phase flip.
Yeah, thank you.
And finally, we can also take the Y gate, just for good measure. So if that. So we have our Y gate here. And here we get then I alpha 1 minus I 0. So this one both changes or flips, and it changes the relative sign between 0 and 1, and it adds a global phase of I, which we don't have. So you can really think of Y as both doing X and Z plus a global phase. Good. So these were sort of the basic gates that we have in principle already seen, but now we sort of formalize them as gates in our circuit. There's a few other gates that are useful to know about. One is the so-called Hadamard gate, which you call H, which is written like this. And just you're thinking, okay, how weird is this? It may be useful to know that we can write the Hadamard gate here, H as 1 over square root of 2 sigma x plus sigma z, meaning that if you wanted to implement this with a Hamiltonian, you just need to turn on both your x and z interaction at the same time, or one after the other, depending on your preferences. But that's a small aside. Just know that every time I now say Hadamard, what I really mean is the application of this matrix on your qubit. And similarly, the S gate and T gates are maybe not used as much as the Hadamard gates, but they will pop up from time to time. So I just put them. And the reason they sort of go together, these three gates, is that it turns out actually that any two-qubit, any single qubit gates that you want to do. So if you just give me a random unitary, whatever, some U, it can really always be written as a product of H, S, and T's in some form, which is actually hard to show, but just trust me that this is true. So, and the way you talk about that in sort of literature is you call this a universal single qubit gate set. Let me talk a bit more about this Hadamard gate, because this is really one of the most important gates that you will see. So we draw it with an H like this. And the reason it is important is that it really acts as what we call a basis changer. So you may remember the states we have looked at before, which are these equal superposition of 0 and 1. Plus 2, 1, and then we have minus, which is 1 over square root 2, 0, minus 1 over square root 2, 1. These ones are the eigenstate of sigma x, right? So if I take sigma x on plus, then I get the state plus. And if I take sigma x on minus, then I get minus. So these are eigenstate of sigma x. So what happens is that if we have our standard state, so alpha 0 plus beta 1, we sometimes say that this is a state in the set basis, right? Because 0 and 1 are, of course, eigenstate of sigma sets. And this Hadamard gate here really changes from this 0-1 basis to the plus-minus basis. So what comes out on the other side here is you can really write that like this. Meaning it changes 0 to plus and it changes 1 to minus. And vice versa, because it turns out that it's actually its own inverse. So if we would then continue and have that Hadamard again, we would just go back to alpha 0 plus beta 1. This will show up in a few instances, and you can really think of it just as like it changes from 0, 1 to plus minus. And that will be very convenient tool to look at. So these are some more gates. The final more gates I want to put in is what is sort of a bit more physical. It's just what happens with these x and y that we saw here. But if we had sort of random times, right? And then we have also seen how that looks, but we can also put that in gate form. But then we need to emphasize what is the rotation angle, theta. So there will be some value sitting here, but that's just. So these are all the so-called single qubit gates that we look at. Now the interesting part, of course, comes when we have more than one qubit. And again, for 2 qubits, we can describe again our gates as unitary operators. And the sort of key thing that people talk about all the time is what we call a C0 gate. So why is it a C0? Let me go over to my whiteboard here. So the C0 gate here stands for controlled not. And not here means just a bit flip. So it's actually in quantum language also the controlled X gate. These are all the same. And, what that means is that if we have a qubit, let's say here we have a qubit A, and then we have a qubit B, this. And now what we can do is we can apply a X gate on qubit B, but controlled on qubit A, and we draw that like this. What that means is that if we have qubit A in the 0 state, then nothing happens. And if qubit A is it one state here? If qubit A is in the 1 state, then we apply X gate. So we can sort of go state by state. So if we would be in the 0, 0 state, for example, and we apply our C0, then because qubit 1 or qubit A here is in the 0 state, we don't do anything. So that just remains 0, 0. If we start in the 0, 1 state, apply the C0 again, the first qubit is in the 0 state, so nothing happens. That's also boring. But now the fun comes. So now let's go with the 0, 1 state. Now the first qubit is in 1. And when we apply the C0, what comes out is now that we need to do an X gate on the second qubit, meaning we need to flip it. So 0 goes to 1. And finally, if you are in the 1, 1 state, you do the C0 again, the first qubit is in 1. So we end up with 0. Like this. So this is what we call the truth table of the gate, meaning what happens to the basic states. And if you write each of them in vector form, you can put one after the other, and you end up with your unitary matrix, which is the one that I've written here. And the notation we use for that, typically in quantum circuits, is something like this. Where this just means controlled, and this one really means not. But we can, in principle, control any type of gate. The CNOT is the one we have that is used the most in most cases, but there's really like no limit to it. So you can have your controlled set gate, for example, and it look like this. That means that if the first qubit is in the 0 state, do a set on the second qubit. If it's in 1 state, you do the set, or you can have a controlled Y. You will draw it like this. Or if you just have a random unitary U, you can also just have a controlled U like this. Meaning just if the first qubit is in 0, you don't do anything. If the first qubit is in 1, you apply whatever unitary you like on the second qubit. And we call them, for example, here controlled set or control U. Yeah. And these are then how we can not only do gates on single qubit gates, but also on 2 qubit gates. And again, think of this as now it's not just a single qubit interaction, but a 2 qubit interaction, for example, exchange interaction that you turn on for a certain amount of time. And that's what gives you these operators here. But with the exchange interaction, we have seen what happens, right? So if we have this sigma x, it's common 1, 2. This is our Hamiltonian. It's half like this, right? We have seen that what that does is it sort of swaps, right? So if we would have t here, we would have probability for 1, 0. And if we start at this point here in the state psi equals 0, 1, then we get this oscillation that I just showed in the lecture. And at this point here, we get the swap gate, which we can also draw a circuit. The way you draw that in a circuit is like this. This is a swap gate. Which is what you have on. So again, this just means that if you come in with a state here, which would be alpha 0, 0 times 0, 0 plus alpha 0, 1, 0, 1 plus alpha 1, 0, 1, 0 plus alpha 1, 1, 1. What this I swap gate is, it sort of swaps these two here, right? So what comes out on the other side is alpha 0, 0, 0. That's not swap plus alpha 0, 1, but now it's swapped. This is 1, 0 plus alpha 1, 0, 0, 1, and then plus alpha 1, 1, 1. So this is the swap gates, which is again one of the interesting gates that you would see. So with that, I think we can move on to our break. And when we come back, let's make quantum circuits that generates these bell states as an example of how we can now use this idea of quantum circuits to generate the states. So see you in hour 9:45.
Could you maybe go back one slide, like the last slide you were on?
This one.
One more? No, there was what came out of the iSwap gate.
Okay, yes, so then go to the whiteboard.
Yeah, thanks.
Good, then yeah, let's go and grab a coffee and then see you in a bit. Hey, and welcome back. So now we introduced the ideas of quantum gates, and now let's try to connect them to some of these interesting states that we looked at in last week. So these are the so-called Bell states. Just as a reminder, the Bell states is a sort of complete basis that we care about, because it's that basis consisting of fully entangled quantum states. So they are very useful to think about. You will also see that in the example of quantum teleportation that I will show you later today. But for now, let's just think about, okay, how can we really create a Bell state using the tools that we have seen.
I'm sorry, I still had a question about
Yes.
the truth table of the CNOT. How are you
Yes.
able to converge that into the matrix for the CNOT? Like, how does it compute?
Yes, okay, I think it's a good question. So it's a bit similar to how we looked at generating let's say the time evolution operator for any state by sort of looking at what happens to each individual basis state. So essentially what you can do is you can take, if you want to find any unitary, you can sort of write it by having sort of the vector, where if you take the vector form of u on your basis state 1, which here is 0, 0. This is sort of, you can think of that as a vector, which you then write sort of in the first column here. So let's give that blue. So this would be sort of a blue vector, and you write that blue vector here. And similarly, you would have u, oh, that was the wrong green. So you would have u on 0, 1, write that as a vector. And that would then be the vector that you write here. Then, okay, we continue, then you would have u on 1, 0, which is then the vector that you write here. And finally, you would have your operator u on 1, 1, write that as a vector. And when you do that, you will get the final vector, which is the one here. And this works for any unitary. So if unitary, you've solved some time evolution, you can do this. If it's just a operator you construct from a truth table, it works the same way. It's you just need to look at what happens to the basis states, write them in a vector, and then you can construct your full unitary like this. Does that make sense?
Yeah, thanks.
Great. Let's actually try to save this. Good. So let's go on to the Bell states here. That's very related to what we just discussed. So let's go to the whiteboard here. So let's start by trying to make the state phi plus like this, 1 over 2, 0 plus 1, 1. So if we want to make that, what we can do is we could maybe start in the state with 0 on both qubits, and then we want to make a 1%. The first thing we notice is that we need to have sort of an equal superposition of 2 states. So what we can do is we can put in a Hadamard gate. Now, what happens at this point here is that now at this point we have 1 over square root of 2, 0 plus 1 here, while the second qubit here is still 0. And so far they are just in product states because they never interact. But this is a good place to start, because now you see that what we would like to do is we want to have here 0 and 0 that matches sort of this part, but the other way is sort of 1, 0. So we want to turn 1, 0 into 1, 1 up here. And that's exactly what we can do with a C0 gate. So let's make a C0 here. Because it's 1 here and 0, that exactly turns this sort of into so 0, 0 stays the same, and then 1, 0, because this one is 1, turns into 1, 1. So then what we get is 1, 1. And ta-da! We now have a Bell state written like this, which is pretty neat. And that's like, now we can in principle just continue on and then construct any of the Bell states that we care about. So let's take the psi minus here, which has almost the same form, except with a minus. Now it looks a bit like this, but except that we have the minus, but we also know an operator that makes a minus into a plus. That's the set gate, right? So it turns out that now we can just write this almost exactly the same way. So we start with this 0, 0 state here. And we start with the Hadamard. Then we do a C0. And now, after this, we are in this phi plus, so we want to change the sign. Here we have the first qubit, for example, in 1 state. Here that's the first qubit in 0 state. So if we do a set gate here, then we just change sign of when the first qubit is in 1. So what turns out here is now, oh, we created the phi minus state. Nice. We can now move on. It's colored a bit more track of things and generate our psi plus state. That's the one that says 1, 0 plus 0, 1. And again, it's like maybe useful to see that if you look at this state, it's almost like this state, except that we flip the first qubit, which tells us that, okay, we can just construct it by making a bit flip operation on the state. So again, we start with a Hadamard, we do our C0, and then finally we do the X gate. And because here we had the phi plus state, the X gate changes this to a 1 and this to a 0. So that's exactly the state we're looking for. So this actually ends up being the psi plus state. And finally, we can make the psi minus, which now is almost guess it without even doing any consideration. So this is 1, 0, minus 0, 1. Because first we have to change sign, and then we have to split compared to this thing. So it's the same thing as if we do both the Z and the X gate. Here. So we start with a Z. So now we would be here. And now if we change this to a 0 and this to a 1, then we would get our the state we're looking for. So we also add a X gate. Ta-da, we have created the sign minus state. So this was maybe didn't look super complicated, but this is really just to show you exactly how to think about this quantum circuits and why it may be a very useful tool. Because instead of really sort of always thinking about Hamiltonians, because we thought about that once, and we know that now we can construct these unitaries, we can start to think of them really as building blocks to build more complicated stuff. So this is what we will do. Any questions to this? No? Then I will do up here and then go back to our slides. Then, before we move on to the final thing I want to discuss today, which is quantum teleportation, let me state a very deep fact about quantum mechanics that is useful to know, which is, let's say I have a quantum state, let's say psi here, equals alpha 0 plus beta 1. Okay, so let's say I want to now make a copy of this state. The first thing you could maybe try to think about is, okay, can we just measure alpha and beta? But this we can't do, right? Because if we measure, for example, sigma z, so if we measure sigma z, what ends up happening is that, okay, we will just get either 0 or we will get 1 with the probabilities alpha squared and with beta squared. So this doesn't actually tell us anything about alpha or beta, it just tells us 0 or 1 if we just add 1, 1. So, okay, you can measure alpha and beta because afterwards you have collapsed the state, it's 0 or 1, and the information about alpha and beta is completely gone. So this doesn't work. But then you're like, oh, but we just learned about the C not right. So maybe we could do something like this, where you would have psi 1 qubit, have the other qubit in 0. Then we can do a C not here, right? And that would sort of almost work, right? Because what would happen is that if the first qubit is in 0, the other qubit stays in 0, and if the second qubit is at 1, we would flip the other qubit, so that sounds a little bit like copying. But what actually ends up happening is that we will end up in the state 0, 0 plus beta 1, 1. And this is generally an entangled state. Meaning there's no way we can write this as 2 separate qubits, both in the state alpha 0 plus beta 1. meaning it doesn't actually clone the state, because again, if we would measure qubit 1, then we would also collapse qubit 2 and so on. So, and this was just examples. You can also, if you really want to be nasty about it, you could prove formally that there really is no way to clone a quantum state. That's just a statement, it's a fact, and it's something that we will make use of. So that's very important. Any questions about this?
Just to make sure that I've understood this correctly. So you're saying that every quantum state is one specific combination of gates. That's the only way to get it.
Yes.
Even if, for example, we have different outputs. For example, if we start with 2 qubits, is it 1? Couldn't there be an equivalent series of gates if you start with two qubits, for example?
Yeah. Okay. So yes, maybe I should say that different. So you generate a quantum state by a quantum circuit, but you can do that. Okay, there's no unique quantum circuit to generate the state. You can do it in different ways. That's true. But once you have a quantum state, the only way of sort of getting it again is to run a new circuit. You cannot just say, okay, I got my quantum state. Now let's just press Control C and then Control V as many times as you want. You really have to run the whole quantum circuit, or maybe a different quantum circuit again to get that quantum circuit.
Oh, okay, that makes sense.
Good. So now that brings us to a sort of let me say this. So that brings us to the what I would call quantum teleportation. Here I draw a quantum circuit, but let's start with a clean whiteboard to motivate it. So let's start and consider 2 people. Typically, we call these people Alice and Bob, because those are nice names. So here we will have Alice. Here we will have Bob. And Alice has a quantum state psi. And now Alice wants to send the quantum state psi to Bob. But it turns out that maybe Alice is in Delft and Bob actually stands on the moon. And it can be very hard to send a quantum state from Delft to the moon. So we have to do something different. And because of this no cloning theorem, Alice cannot just make a copy of a state and try to send it to Bob and see if it succeeded and then continue like that, because there's no way of copying this thing. So we have to do something different. And the way you do it is you make a Bell state that is shared between Alice and Bob. So put here a state. I want to have this state by plus. So this is a 2-qubit state, and half of it Alice has, and the other half Bob has. So essentially what you can sort of think of is that before Bob traveled to the moon, Alice and Bob made an entangled state, and Bob kept his part of the state in the pocket. So now they have this entangled state. That is, yeah. And now we can use this entangled state to actually send this qubit to Bob. And the way we would do it is we draw this quantum circuit. So we would have our state psi here. And then we would have our 2-qubit state, 5 plus here. And now you can think of it as sort of this part here being Alice. And then this qubit here is Bob. And what Alice does is she first applies a C0 gate and then a Hadamard gate. And the way you can sort of think about this is that what she does is sort of making a reverse of creating a Bell state. Because we saw here, right, that here, this is how we create a Bell state. So what Alice tries to do is sort of uncreate a Bell state, but not on the actual Bell state, but on half of her Bell state and the sort of pressure state that you want to send to Bob. And then after that, she actually does then a measurement. We did not talk about measurement in quantum circuit, but the way we typically draw it is like this. So this looks like a meter, and you measure it like this. And now, after this measurement, what happens is that now we can actually see that Bob will have the state that Alice initially had. So let's look at how that really works. So what we really start with is this state psi that Alice has, and you can sort of tensor it with this psi plus here. So now it's a 3-qubit state, but it really works this product. So if we write that out sort of slightly more explicit, so we get alpha 0 plus beta 1, and we tensor the product that with 1 over square root of 2 0 0 plus 1 1, and we can write that by just putting it all together now. So we get alpha 0 0 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1. Like this. Yeah, like this. Okay, so now we will do this C0 here operation, which has the first qubit here, which is the precious qubit, as the control, and then it has the target on half of this belt. So what happens is that this state, let's just call it here. So now we are sitting here. And at this state, the state is now, we can sort of go from here. So we start with our square root of 2. And then we get alpha, okay, the 0 0 0 doesn't change anything, right? 0 0 0 plus alpha, sorry, alpha 0 1 1 also doesn't change. Then we get plus beta 1, and now we change this 0 to a 1. 1 0 plus beta 1 0 1. Now we do the Hadamard gate, which is here. So now we will be at this point. That's the Hadamard. And as we discussed, that change takes the 0 state here to the plus state. That's the idea. So let's maybe for convenience just write now the alpha here. We can take the 0 state out of the parentheses, so we get the plus state, which is 0 plus 1 over square root of 2 0, 0, plus 1, 1. And then here, the one state here now becomes minus state, so 0 minus 1, square root of 2. And then we have the 1, 0, plus 0, 1. Like this. Good.
Didn't you forget a beta somewhere in the?
Yes, I did that. That's good. There should be a beta here. Good. So that's the state. And now we can think about, okay, what happens now if Alice tries to measure these two qubits? So let me make a use right here, and then we just repeat the thing we just have written down. So we have the 1 over square root of 2. And here we have the alpha 0 plus 1 square root of 2, 0, 0 plus 1, 1. And then plus beta 0 minus 1 square root of 2. And then we get the, how was it again? It was 1, 0 plus 0. 1, 0 plus 0, 1. So now we can collect essentially what all the outputs of Alice would be. So we essentially just rewrite this. We can take this 1 over square root of 2 outside parentheses, get 1/2. And then, okay, the first option Alice could get was 0, 0. So we see that there's a 0, 0 term by combining this. And there's also a 0, 0 term here by combining this. So we get a parenthesis here, which is then alpha times 0, 0. I'm sorry, times 0 plus, and over here we have a 1, so that's a beta times 1. Then we move on to Alice could also measure 0, 1. We see that that term is by taking this term here together with this, and it comes by taking this term together with this. So what we get is alpha times 1 plus beta times 0. Now, the next thing she can measure is 1, 0. That comes around by having this one and this term. And from this term and this term. So if we continue that state and combine, we see that now we get alpha. So here the last qubit is 0, so 0. And here we have the minus in front, so we get minus beta 1. And finally, what Alice can measure is the 1, 1 state, which we see can come from having this term, and this one, and this one, and this one. So here we see that we get alpha, and this one is a 1, so we get alpha 1 plus, no, sorry, plus, here's a minus, so minus beta 0. Like this. So this is our state. So if we let's draw a quantum circle again, just to remind us what we are at. So we started with psi, then we did C naught gate to half of our Bell state. Then we did a Hadamard gate up here. And now we did these measurements. Here, measurement here. And now the first thing we see is that, let's say we measured 0, 0, 0 here and 0 here. What happened is that, okay, this state now for Bob, this is actually the state we wanted, right? So this is psi. So if Alice measures 0, 0, then we know that Bob already has the state that we wanted to send to him. So then we would win. Right? But of course, we could also have measured, let's say, the next thing here, 0, 1. And if you look at what Bob has, is Alice measures 0, 1. It's almost the same, except that now 1 and 0 are flipped. So what we can do is we can apply a X gate on Bob's qubit, controlled on the output of this. So this is now a control gate. I now draw this with double. Yeah, so that means it's a classical number because we did a measurement. So it's now based on the measurement output, not on the qubit. So this is quantum. And if I do like this, that means classical. That's just the rotation. So that just means that what Alice does is she measures what is qubit, and then if she gets 0 or 1, she sends that information sort of by a classical channel, not a quantum channel, but just like sends a text to Bob. And then Bob, if he's told by Alice that this output was 1, he does a X gate, which will make this state here into a into the target state that we wanted, which was alpha 0 plus beta 1. Of course, there's also other outcomes. It could be 0 or 1, which again, we almost have what we need, except we need to change this, but we also know how to do that. That's a set gate. So here, Bob could also apply a set gate, but now, depending on what classical information we get from the measurement of the first qubit. And now we can see that in the last instance here, where we have 1, 1, it actually works out that, okay, first we flip them, and then we change sign, so we are exactly where we want it to be. Such that when we go in the end here, no matter what outcomes Alice measured, when Bob does these operations, we get the state psi at the end. So at the end here, Bob always has psi, which is pretty cool. That means that no matter what state Alice started with here, she can just do 2 gates and some measurements, send the outcome of the measurements to Bob, and then Bob gets the state psi. And we didn't need to send any quantum states through space. It was just, the only requirements was that we started with some entanglement between Alice and Bob. This also tells us an important fact about, let's say, quantum communication or quantum teleportation in this case, in general, which is maybe sort of slightly in contrast to sort of how teleportation is sometimes depicted in say, literature. Because what people sometimes get confused about is that we have this idea that Alice and Bob would in principle be as far away as possible. Earth and the moon, or like on the other side of the solar system, whatever. And this protocol would still work, but it only works because we send this classical information here from Alice to Bob. We don't send any quantum information. We only send the classical information, but we still need to send that. And classical information only travels by the speed of light at maximum, meaning this whole protocol of sending quantum information also only works like limited by the speed of light, meaning there's no way you can sort of instantaneously share information faster than the speed of light. It's because you need this classical communication, which is also key to know, but nonetheless, it's still pretty cool that we can, without ever measuring the state that we're interested in, we can actually send that state over infinitely long distance by just sending 2 bits of classical. So this is really cool. It's really a key thing about quantum communication is this ability to send quantum states just using a bit of measurements for classical communication. Cool. Any questions to the quantum teleportation protocol?
Why does there need to be a classical signal?
Why it needs to be there?
Yeah.
So, okay, I can give 2 answers to it. The first answer is that if you look at this state, so if you take the state that we have here before we sort of use the classical information, so this state that I drew here, that's the state essentially at this point. And if you look at that and then look at what state Bob has, is sort of alpha plus beta, or it's alpha plus beta but swapped, so beta plus alpha, or it's alpha minus beta, or it's beta minus alpha. Meaning it's actually completely random what he has, because if you take the average of these 4 states, you actually get, no matter what alpha and beta is, you get that this is just completely what we call a mixed states, in the sense that you don't have any information left, because it's equal chance of getting 0 and 1 in this case, because you sort of randomly has a bit flip or phase flip. So without this classical information, what Bob has is completely random. We only get the state psi if we take this classical information into account and makes the bit flip here, the phase flip here, and both down here. Then we are back, always have psi, which is the alpha plus beta state. And we could really only do that if we knew what Alice measured. Does that make sense?
Yeah.
Okay, great. The second answer is maybe a little more redundant, or maybe more like conceptual, is that if we didn't need this classical information, then we could actually use quantum mechanics to send information faster than light, and that would sort of break down all of physics. So, but that's more like a philosophical answer, but the technical answer is that we can really see it from this equation that Bob only gets the state we want him to have after he acts on this classical information. Good. Other questions? I know this.
I have a question.
Yes,
Does it matter which Bell state is used?
You can use all of them. The protocol will look slightly different depending on which Bell state you have, but you can use all of them. I thought the calculations get a bit easier if you use this state, but there's nothing that prevents you from using one of the other Bell states. Good. Now, the final thing I just want to say about this is that if you look at the probabilities here for measuring, for example, 0, 0 for Alice, you can calculate that from this state, and it turns out to be 1/4, because you have 1/2 here in front of 0, 0. And here you have alpha and beta, but alpha squared plus beta squared, that's just 1, so you get 1/2 squared, which is 1/4. And similarly, you also find probability to get 0, 1 is 1/4. The probability to be 1, 0 is 1/4, and finally the probability to be 1, 1 is also 1/4. Which, okay, maybe that doesn't sound very deep, but it's very key to notice that this is independent on alpha and beta. Meaning it doesn't really matter what state psi we started with, Alice will always have the same probabilities for outcomes in her part of the protocol. And this is really key, meaning, so another way of saying this is that Alice did not learn anything about alpha and beta from doing this protocol. And it sort of goes also the other way around, that if she sort of by accident learned a little bit about alpha and beta, then you would quote unquote destroy the quantum information because you project the state, and then there would be no way of transmitting the state to Bob. And one of the really key challenges when we are building quantum information is to sort of prevent these accidental measurements, not sort of by us, but you also don't want, it's not only humans that can measure, right? And like, measurement just means that something learns about your quantum state, and that something could be the molecules around your qubit that sort of accidentally picked up a little bit of alpha. And if that happens, you cannot send the state perfectly. So you only have perfect state transfer if your protocol does not reveal anything about your state. This is a very deep point, so if it's not completely clear, that's okay. But just want to mention this.
I was wondering, in practice, how prone to faults are these kind of systems?
Yeah, so that depends a lot on the experiments that you do. Sort of a typical, let's say, good protocol that people have implemented over long distances have sort of what we call fidelity. That's the sort of probability that it all works out well, sort of above 90%. That's sort of very good, state of the art. If it's sort of very small distances, people have done this with sort of more like 99% fidelity in sort of a small quantum processor, but this is sort of the ballpark where the numbers are at. Here in Delft, I think this was done sort of with over many meters of distance. I think maybe they even went to sort of 1 kilometer. I'm not 100% sure of the numbers there, but there they also got sort of more like 80% fidelity, which was sort of over a kilometer distance, which is, the fidelity is not very good, so it's not perfect yet, but they are now really doing it over. I think that the plan is to have sort of a node in Delft, node in Hague, and then have one in Amsterdam, and really do this thing between the different sort of nodes in the quantum network. And for those systems, the fidelities are close to 90%. The success rate that this really goes as you want is around 90%. Good. With that, I will now save this and then stop sharing.